In July, NASA's Asteroid Terrestrial Impact Last Alert System, or ATLAS telescope, in Chile, made a groundbreaking discovery: a potentially billions-year-old icy celestial comet.
It began as a quiet watch, the kind NASA does best when the public isn't paying attention. No countdowns, no rocket fire, no press conference stage lights. Just a handful of scientists staring at fresh sky survey data, tracking a fast-moving point of light that did not belong here. They called it 3I Atlas. And even that name carried a warning, 3I, as in a third interstellar object, a third visitor from outside the Sun's family. And Atlas, as in the network built to catch sudden surprises before they slip away. At first, 3I Atlas looked like what you would expect from a distant traveler, faint, stubborn, and indifferent to our excitement. But the closer it came, the more it refused to behave like a normal asteroid or comet. Its trajectory was unusual enough to light up debate. Its brightness did not rise smoothly the way you would expect from simple geometry. And then, in a window of time so short most people would miss it completely, something happened that forced the conversation to change. The object flared, not gently, not gradually. It brightened sharply, as if someone had cracked a sealed container in the vacuum and let a cloud spill out into sunlight. After that, it did not fade back in a clean, predictable curve. It faded unevenly. It flickered in behavior. Observers saw hints that its rotation signature might have shifted, the kind of subtle fingerprint change that makes astronomers sit up straight because it suggests the body itself may have changed shape or surface or balance. That is when the rumors took off. Because in small body science, when something brightens suddenly and the light curve starts acting like it belongs to a different object, one hypothesis rises fast to the top of the list. A collision, a strike, an impact, not necessarily dramatic in size but dramatic in physics, because at interstellar speeds, even a small object can hit like a hammer. The internet did what it always does with interstellar anything. It reached for certainty. It reached for cinematic language. It started speaking as if NASA had confirmed a crash, as if we had watched two objects collide in real time like a slow-motion sports replay. But NASA did something unusual. It spoke carefully, not to declare a verdict, but to anchor the moment. To say, in essence, the data pattern is consistent with an impact, even if not uniquely proven yet. And yes, this is worth paying attention to, because if an interstellar object truly collided with something while we were watching, that would not just be a headline. It would be a rare natural experiment, a chance to learn what these fast strangers are made of, how they are built, and how they respond when the solar system stops being a quiet hallway and becomes an active environment. So the real story is not that NASA confirmed a mystery crash with full certainty. The real story is that something changed fast enough, and strangely enough, that the most grounded scientific reading points toward a physical event, and one of the cleanest explanations is a collision with a mystery object we likely never cataloged in the first place. And if that is true, even if only in the most conservative version of the scenario, then 3I Atlas is not just passing through. It is interacting, it is being altered, and for a brief moment, it may have opened a window into material that was once sealed inside the cold history of another star system. Before we get into what NASA actually meant by breaking its silence, we have to understand why 3I Atlas was already a big deal, even before anything hit it, because the collision talk only makes sense when you realize what this object represents, and what it could mean for how crowded interstellar space really is. If you like this kind of story, where the universe refuses to behave neatly, make sure you hit like and subscribe, because this is exactly the kind of mystery that evolves in real time. Now let's start with the foundation. 3I Atlas was already changing the game before the collision rumor ever appeared, because the idea of interstellar visitors used to feel like a once-in-a-lifetime event. The first ones felt like cosmic lottery wins. A strange object shows up from outside, we scramble for observations, and by the time we understand what we are looking at, it is already leaving. The sample size stayed painfully small. That is why debates around the earlier visitors never really closed. Every detail became a tug of war. Every interpretation carried too much weight because there were too few examples to stabilize the science. But a third detection changes the psychology and the math at the same time. If 3I Atlas is truly the third identified interstellar object, then it strengthens a simple but profound argument. These bodies are not freak accidents. They are a background population. A steady galactic drizzle of fragments, leftover building blocks thrown out of star systems during chaotic planet formation, drifting for ages until one passes close enough to be seen. The reason we did not see them before might not be because they were not there. It might be because we were not looking well enough. That is where the Atlas network matters. It is designed to scan wide areas of sky quickly, looking for fast, faint, changing targets. In other words, it is built for exactly this problem, catching objects that appear suddenly and evolve quickly. When a system like that is tied to the discovery, it adds context. It suggests the detection was not a lucky accident from a casual glance, but a product of modern surveys doing what they were designed to do. And that matters, because interstellar objects do not give you time. They move fast. Their window is short. When they are discovered late, their best data phase can be gone within days or weeks. A third object caught with better infrastructure is not just another dot on a chart. It is a signal that the era of systematic interstellar detection may be beginning. And if that is true, then the implications multiply. It means we can start asking population questions instead of one-off questions. Not just, what is this weird object, but what is the distribution of shapes, compositions, and behaviors among objects ejected from other stars? Do they tend to be volatile-rich like comets or rock-dominant like asteroids? Do they form tough, coherent bodies that survive long travel, or are they fragile aggregates that only stay intact because interstellar space is mostly empty? Even the Manhattan-sized framing, whether perfectly accurate or not, tells you what the public instinctively grasps. This is not microscopic dust. It is a substantial traveler, big enough that its response to heating, stress, or impact would be measurable, and big enough that scientists would care deeply about its structure. And here is the key. The most important scientific value of an interstellar object is that it is not from here. It is not a member of our family. It is not a relic of our own solar nebula. It is a foreign sample, a piece of another system's leftovers. And every hint we can extract about it becomes evidence about how universal or how varied planetary building blocks might be across the galaxy. So before a collision ever enters the conversation, 3i Atlas already carried enormous weight. It was another chance to expand the sample size, another chance to refine the models, another chance to compare this visitor to the earlier ones and see whether they were outliers or the first glimpses of a diverse population we are only beginning to notice. And then the object did something that made the whole story tilt. Because discovery is one thing, behavior is another. And when 3i Atlas changed suddenly, it was not just giving us a third data point. It was offering something rarer, a live event, a moment where physics happens fast enough to be seen. Which brings us to the part that triggered NASA's response. The sudden change NASA could not ignore. Astronomers are used to slow changes. Most small bodies brighten gradually as they approach the sun, simply because they get closer and reflect more light. If a comet becomes active, its brightness rises in a more complex way because gas and dust expand into a coma that catches sunlight. But even then, there is often a rhythm, a curve, a pattern. What made 3i Atlas different was the sharpness of the change and the way its brightness evolution refused to settle into a neat explanation. Observers saw what looked like a spike, a rapid brightening that did not match the gentle climb expected from distance changes alone. Then instead of fading smoothly, it faded unevenly, as if the object's reflective area had expanded and then dispersed in chunks, or as if the surface properties had been abruptly altered and were now stabilizing. That is where light curves come in, and they are more than just a graph. A light curve is a fingerprint. It is the way an object's brightness changes over time, and it encodes shape, rotation, and surface behavior. If an object is elongated, it brightens and dims as it spins, presenting different cross-sections to us. If its surface has patches of different reflectivity, you can see that too. If it suddenly releases dust, the signal changes again. Because now you are not just seeing the nucleus, you are seeing a cloud evolving around it. So when astronomers say the rotational signature appeared to shift, that matters. It suggests that something about the object's balance or surface or shape may have changed. And there are only a few mechanisms that can do that quickly. One is a sudden outburst, where trapped volatile pockets erupt, blasting dust outward and changing the visible profile. Another is rotational instability, where spinning speeds up until surface material sheds, like a loose gravel pile flinging stones off the edges. But the cleanest mechanical explanation is a collision, because an impact can do several things at once, and it can do them in an instant. It can excavate dust and expose fresh material. It can change the effective cross-sectional area. making the object reflect more light. It can alter rotation by transferring momentum, nudging the spin rate or even the spin axis. And it can produce a dust cloud that temporarily makes the object appear much larger and brighter than it really is. That is why the collision hypothesis rose so quickly. Not because it is the most dramatic, because it is efficient. It explains an abrupt mechanical reconfiguration plus a dust release in a single event, and it aligns with what we know about high-velocity encounters. And the mystery object part is not a science fiction flourish. It is a practical reality of our observation limits. The inner solar system is filled with countless small fragments that are too tiny to track individually. We model them statistically. We know they exist because we see their collective effects: meteor showers, dust bands, impact craters, and the steady background of micrometeoroids that spacecraft have to endure. But we do not have a catalog of every meter-scale rock. So if 3I Atlas passed through a region with elevated debris density, or if it simply had bad luck, it could have been struck by something small, something anonymous, something that would never show up on its own in a telescope. And at interstellar speeds, small stops meaning minor. This is the part that feels counterintuitive until you sit with it. Energy scales viciously with velocity. A small projectile moving extremely fast can deliver enormous energy on impact. It does not need to be a mountain to make a visible signature. At those speeds, even a modest object can excavate dust in a way that makes the target flare in brightness, because the dust cloud increases the reflective area far beyond the original nucleus. So a collision does not have to mean two giants crashed. It can mean a fast traveler from beyond the sun's family got clipped by a relatively tiny piece of local debris, and the resulting dust plume made the whole system light up like a signal flare. Now here's where NASA's response becomes important, because NASA did not claim a smoking gun. NASA acknowledged that the data behavior is consistent with impact-driven change, while keeping alternative mechanisms on the table. That restraint matters because brightness spikes can have multiple causes, and early data is always messy. Different instruments have different calibrations. Background stars can contaminate measurements. Rotational coverage can be incomplete. But even with those caveats, when you see rapid brightening, uneven fading, and hints of a changed light curve fingerprint, you do not ignore it. You treat it like a physical event, and you chase it fast. Because interstellar objects do not wait around for you to finish debating. They pass through and the window closes. So in the next section, the story becomes sharper. If it was a collision, what kind was it? The most conservative explanation is that it was struck by a local solar system fragment, and that alone would still be scientifically valuable because it could expose the internal nature of the visitor. And that is where the real implications begin to stack up. What a collision really means when speed is the main weapon. When most people hear the word collision in space, they imagine two large objects smashing together like slow-moving boulders. That picture feels intuitive, but it is misleading. In space, size is often less important than speed, and interstellar objects operate in a very different velocity regime than most native solar system bodies. 3I Atlas is not drifting gently. Its trajectory tells us it is moving fast enough that even a tiny impactor can deliver energy that far exceeds what its size might suggest. This is one of those moments where physics breaks common sense. Kinetic energy scales with the square of velocity. Double the speed, and you quadruple the energy. At interstellar speeds, that scaling becomes brutal. So when scientists say a meter-scale object could produce an outsized effect, they are not exaggerating. A small fragment striking at extreme relative velocity can excavate surface layers, shatter brittle material, and eject clouds of dust in an instant. That dust does not need to be massive to be bright. It only needs to be numerous and well-placed to scatter sunlight efficiently. This is why a collision does not have to leave a dramatic scar that we can see directly. It leaves a photometric signature, a sudden increase in brightness, a change in how the object's light fluctuates as it rotates, a dust envelope that expands, thins, and evolves under solar radiation pressure. From an observational standpoint, this is powerful. Dust acts like a temporary amplifier. It turns a small physical event into a visible one. The reflective area increases far beyond the original solid nucleus, and for a brief window, telescopes see something much larger than what actually exists. That window is fleeting. Radiation pressure pushes the smallest grains away quickly. Larger grains disperse more slowly. The brightness fades unevenly as different particle populations separate and spread. This uneven fade is exactly the kind of behavior that raises eyebrows in the data, because it does not look like simple geometric dimming. Another reason collisions stand out is that they can alter rotation almost instantly. Momentum transfer does not care about narrative pacing. A hit can nudge spin rate, tilt the axis, or destabilize surface layers that were previously marginally stable. When astronomers notice changes in rotational signature over short time scales, they naturally ask what could have changed the object's mechanical state so quickly. A collision answers that question cleanly. It also explains why the identity of the impactor remains unknown. The solar system is full of debris too small to track individually. These fragments do not announce themselves. They exist statistically, inferred from their cumulative effects rather than seen one by one. When one of them collides with something fast and unusual, it briefly steps onto the stage and then disappears again. In that sense, the mystery object is not mysterious because it is exotic. It is mysterious because it is ordinary. And that makes the collision hypothesis feel less dramatic, not more. It places 3I Atlas into a real environment, one where chance encounters happen, even if rarely, and where velocity turns small actors into consequential ones. But this is not the only plausible story. And to understand why NASA kept its language careful, we need to look at the most conservative version of events first, before considering anything more daring. The grounded explanation, a local solar system impact. The simplest explanation that fits the observed behavior does not require anything exotic beyond what we already know exists. In this scenario, 3I Atlas was struck by a small fragment native to our own solar system. A piece of debris that never had a name, never had an orbit precisely measured, and never would have been noticed on its own. This is not a stretch. The inner solar system contains regions where debris density is slightly elevated due to orbital resonances, asteroid family remnants, and long-lived dust populations. These fragments are not evenly distributed. They cluster statistically along certain paths. A fast-moving interstellar object passing through one of these regions increases its odds, modestly but meaningfully, of a chance encounter. If that encounter happens, the physics unfolds quickly. The impact excavates surface material, lofting dust outward. Fresh material that has not been heavily processed by radiation or micrometeoroid scuffing gets exposed. The dust cloud expands, briefly increasing reflected sunlight. To telescopes, the object appears to flare. Then the cloud evolves. Small grains accelerate away. Larger grains linger. The brightness fades unevenly. The light curve becomes messy, because it is no longer a simple signal from a rotating solid body. It is now a composite of nucleus rotation plus changing dust geometry. This version of the story fits comfortably within known physics. And even in this conservative framing, the scientific value is substantial, because how 3I Atlas responds to an impact tells us about its internal structure. Is it a coherent chunk of rock or ice that sheds only a limited amount of dust? Or is it a loosely bound aggregate, a rubble pile assembled gently in a different star system, held together by weak gravity and surface cohesion? A fragile object would likely produce a broader, longer-lived dust envelope. A tougher object might show a sharper spike and faster recovery. The rate at which the dust thins, the way the brightness fades, and whether the rotation stabilizes or continues to wobble all provide clues. This matters because interstellar travel is harsh. Long exposure to radiation, cosmic rays, and tiny grain impacts can alter surface layers dramatically over time. Some models suggest interstellar objects develop insulating mantles that hide their true composition. A collision can puncture that mantle, exposing material that has been sealed away since the object formed. So, even a mundane local impact becomes a mechanical excavation. It turns a passing visitor into a briefly open sample. And that is why scientists are excited without needing the impactor itself to be exotic. The response of 3I Atlas is the story, not the thing that hit it. But there is another possibility that scientists cannot ignore, even if it remains speculative, because once you accept that interstellar objects are not unique flukes, a more daring question naturally follows. What if the thing that hit it was not from here either? The bold hypothesis, an interstellar on interstellar encounter. This is the version of the story that ignites imaginations, and for good reason. But it is important to understand that it is not science fiction. It is a hypothesis grounded in what we know about planet formation and gravitational chaos. Planetary systems are messy. During their early evolution, giant planets migrate. Orbits destabilize. Countless leftover building blocks are flung outward, some into distant orbits, some completely ejected into interstellar space. If most star systems go through this phase, then the galaxy should be seeded with fragments of many sizes, drifting between stars. For a long time, this was theoretical. Now we are starting to see them. A third interstellar detection already suggests that the detection rate is rising as surveys improve. That alone implies a background population that is larger than once assumed. In that context, the idea that two interstellar objects could cross paths near our observational window is improbable, but not absurd. Improbable events still happen, and science does not dismiss them outright when the conceptual foundation exists. If the impactor were also interstellar, the implications would be extraordinary, not because it would be dramatic, but because it would be informative. Two foreign objects interacting under our instruments would act like an accidental experiment in galactic archaeology. The debris from such a collision could carry chemical signatures that differ subtly from typical solar system material. Even small differences would matter. Spectral hints of unusual elemental ratios, distinct carbon compounds, or unexpected mineral structures would suggest formation in a different protoplanetary environment. It would also sharpen estimates of interstellar object density. If such encounters are even marginally plausible within our detection window, then the background population might be richer than models predict. But scientists are careful here. There is no direct evidence yet that the impactor was interstellar. No distinct trajectory, no independent detection, no smoking gun. That is why NASA has not elevated this idea beyond speculative discussion. Still, it remains on the table as a hypothesis worth testing, not believing. And what makes it compelling is not the coincidence itself, but the leverage it would offer. Correlated trajectories, shared dynamical properties, or unusual dust chemistry could all help refine how we think about material exchange between star systems. Whether the impactor was local or interstellar, the key takeaway is the same. 3I Atlas may have been mechanically awakened, and that awakening gives scientists access to information they rarely get from objects that spend most of their lives silent, cold, and sealed. In the next section, that access becomes the central theme, because the real prize of a collision is not the violence of the event. It is what it reveals once the dust starts to speak.